Hello, everybody, and welcome to Lab 2. My name is Kyle Shorey, and yeah, let's get into it. So first off, I'm going to introduce the lab, go through the procedure, the models, the errors, and then what if and what it means, and then the conclusion. So to start off, our lab focuses on two electrically charged pieces of tape and how they interact when put within a close distance of each other. Our job is to compare an observed experimental trial to a predicted computational model. We want to expand upon our analysis from Lab 1 by focusing on the tape as a line of charges rather than just 2-point charges. And in this experiment, we are aiming to verify like Coulomb's law, and we also know that like charges will repel each other while unlike charges will attract each other. Some of the equations we'll use: Coulomb's law, force of gravity, electric force, and rod electric field. So here is a free body diagram. You can see the top line of charges and the bottom line of charges at equilibrium, as the electric force at the top line is equal to the force of gravity on the top line. So procedure, honestly, pretty much the same procedure as lab 1, except the only place that we're changing it up now is within the glue script code instead of the actual experiment. Some of the assumptions we made while running the experiment are the negligible air resistance. We assume that each piece of tape had the same electron distribution across the entire piece. We assume that the charges on the tapes could be reduced to multiple point charges evenly. And we assume that each U-tape was made had about the same length, about the same amount as charge evenly distributed along the length of the tape. Some of our initial conditions: you can see the tape mass, the tape length, G, Coulomb's constant, and Q, which is the charge. Here are the equations we use to get Q. So force of gravity is going to equal mg, which is also going to equal the electric force. The electric field for the rod is going to be this equation right here: k times q over r times the square root of r squared plus l over 2 squared. And Coulomb's law over here, and then which is used to create the electric fields at point charge. And then we have electric force here. So as you can see here, the electric force equals the electric field times Q. And we know that the electric field is this for a rod, and multiply it by Q, and set it equal to f of G to solve for Q. Here's the computational model. So as you can see, we have the functions for E field, which calculates the electric field for a point charge, and then line charge, which creates a line of charges. So here you can say we had to create two line charges, the top tape and the bottom tape. And then for here in this for loop, you can see that we had to calculate the rod electric charge, or rod electric field for every single point in there. And then, yeah, here are the glow script results. So as you can see, the electric force and the gravitational force are pretty much equal. Um, and then here in green, you can see all of the individual point charges, electric fields. The potential errors, so maybe a way to do measurements at the same time could, by using a more permanently charged item, could make it more accurate so that we lose less charge to the environment. There were likely uneven charges, which were not reflected in our calculations, and small rounding errors can make a big difference considering how small the numbers we are using are. And then the what if slash what does it mean? Uh, what if we had modeled each of our tapes as a single point charge? This is what we did in the first lab. And in the first lab, as you can see, we got a point charge of 9.567 e to the negative 9. And for the line of charges in this lab, we got 3.044 e to the negative 9. And why do these estimates differ, and which one is closer to the real value? Well, they differ because you're using less precision, which with the single point charge rather than the line of charges, because it's generalizing everything down to one point versus breaking it down into a bunch of smaller points. And because of this, we know that the Q for the line of charges is more likely to be closer to the actual Q value, because it's broken down into multiple pieces and doesn't just generalize it down to a single point. And yeah, thank you for watching.